That's right. Equally unfair. About the fairest thing you'll ever find in life is when everybody else is equally unfair. And you won't find that either. It's a faculty lecture, which actually I'll start. All right, well, hey, let me go ahead and begin our little class here together. I'll start with a couple of pieces of news. Probably the first one that many of you asked about. I went ahead and before even getting your input on it, thinking you would do the same thing, and so I better ask. But the morning class was really begging for the test to be postponed after, well, begging's a little strong, but they were hoping they would say it was the advantage of waiting till after spring break. And I pressed them on it. I questioned it. I said, are you sure it's not going to make you forget it over spring break? Or they told me they were all engineering students and had no social life, so it wouldn't be a problem. I think it was almost the exact words. And I also, and I'll say this to you too, I said, well, the other challenge I have is I'm going to be given a Physics 121 test that week too, so I may not have enough time over the weekend to grade both of them. What if it took me a little extra time to get it back? And they said that would be better too. So they said all that, and I said, okay, then Tuesday when we come back from spring break works for me, if that works for you, if you don't mind me taking a little longer to grade, and you promise not to forget the stuff and to study and all that good stuff. So, how about you guys? When do you guys want the test? Today? But I went ahead and told them after spring break. You guys asked about it. I think you two asked about it last time. So, is that like a good game plan? Tuesday after? All right, good. And so that's the game plan then. We're going to do the test on Tuesday when we come back here. All right? That's announcement number one. That means Don, who had been telling a lot of you that the review would be this Sunday, it won't be this Sunday. It'll be the next Sunday. So, remember that. You're going to have to remember it the whole spring break, that the Sunday at the end of spring break, if you want to go to the review, come here at 1 o'clock on that Sunday there, okay? And Don said that he knew some people would be traveling and may not be able to come back, so yeah, he made sure he wanted me to tell you that he does have the practice test with him, and he's got the answers worked out, so make sure you pick up that sometime next week too, so that if you don't make it back for a review on Sunday, you can at least have that with you, and that'll give you next week to maybe look it over yourself and ask questions. So that's announcement number one. Test postponed a little bit. Announcement number two is I've been sending these around, got a couple today here, and so I'll say it again that this is that time of the year where we are looking for faculty nominations, that is the outstanding faculty. And so I'm going to take this one and put it in my notebook and put it with the other ones. Some of you have already given me one. Others of you, I think, are planning still. Others of you maybe aren't planning. If you aren't planning, think about it. That'll give you something to do over spring break there. And I fill out that little form because, as you know, we didn't have a lab this week. Oh, maybe I should say, so there's not a lab this afternoon for those of you in the afternoon class, but the lab was canceled because of the faculty lecture. Then I was down over there in the gym all day yesterday, and today I won't have that obligation, but I'll have other obligations. So again, we're still not having a lab. So with that said, let's finish up chapter 22 and actually get to what I think, and I hope I'm wrong here, I think is really the hardest of all three semesters, the concept of entropy. What is it? What does it really mean? And the second law of thermodynamics. I started this process by teasing you to it. Now I want to spend the next 45 minutes to an hour to try to get you to understand entropy, and then we'll spend the time after that calculating the entropies and the efficiencies. I promised you also that as we got started, I would put these engines back on here. So let me change the diagram. This was the diagram we had at the end of the last section, but let me go back to the Carnot cycle here, the Stirling engine, and point out what we just kind of barely got to. We were a little low on time here, but let me set it up here again. Let me take the ice tray, or the pan, let me fill it with ice, so now it becomes an ice tray here. And so here is my cold environment. My hot environment is going to be the room. And so if I were to place this on the cold environment here, the room, and let me get some of the splashed water off of it so that it stays hot on the top. But the top is hot and the bottom is cold. And so what's going to happen is energy is going to flow and hit those molecules. Make the molecules go faster. The faster moving molecules hit that piston and push it down. And that's where the power comes from. That's where the energy is being used to make work. And so heat energy comes in, pushes on those, and does work. But in addition to that, when the displacer is moved up to here, the molecules come into this area, they cool down, they slow down, giving heat to the cold environment. And so heat comes in, work is being done, energy flows out. We left on Tuesday with this picture that if this is the engine, then what is happening is energy is flowing in. I'll call it the hot environment, Q sub H. Energy flows in. Then the goal of the engine is to do work. That's the best part of this engine. It actually does work. And we would often say this, that could I get more work out than heat energy I put in? You would hopefully tell me no. And why not? Conservation of energy, right? This is the first law of thermodynamics. Okay, so you can't have this, so then I'd go to the next step. Can the amount of work coming out of this engine be equal to the amount of heat? And hopefully again you're saying no, but why?
Because QC is not zero.
And this is the second law of thermodynamics. This would involve an entropy. And that is where we need to spend the next hour talking about entropy. What is the meaning behind it? And why then could I not get this to be what we would call 100% efficiency? So I'll put a question mark and cross it out. And so I can't have this from what we call the first law of thermodynamics, and I can't even have this because what I call the second law of thermodynamics, which is what I want to get across to you in the first hour, and then use the next hour to do examples, and then use Tuesday to do more examples. Then since we're not having the test on Thursday, I guess we'll start optics, and then when we come back on the Tuesday after spring break, we will have the test there. But don't forget this other piece of this. So just like energy flows in, there would be a change of entropy. And I can't remember, did I actually use the symbol S for entropy yet? Okay. And so the standard symbol here, we're going to use S. So S for entropy. And so there would be this change, this increase in entropy into our engine. Okay? And also, and I think I mentioned this also, is that the whole reason then I could not have all the energy coming out is because then I have to take that entropy out. To get this engine back to its starting point, I got to have everything back to its same place. Not only the same energy, but also the same entropy. And so this entropy is a state function, and we got to get the engine back to its starting point. Now, this one probably cooled down enough. So let me give it a start. And so that one will hopefully start going. Did you have a question? Oh, it does have units. Hang on though. All right, give me, like I said, an hour to develop what entropy is. And I hope I don't talk too much. And like I said, I hope the entropy is the easiest for you, because for some people it is, but I would say for most, this is probably one of the hardest ideas, really. It is the most abstract. The second law of thermodynamics is, to me, harder than the second law, say, of Newton's second law of motion, definitely by far here. But I do want to keep emphasizing there's two things going on at the same time. That's why, if you remember, I did this little experiment for you. I tried to do something like this. I tried to say, could this object crash and make more heat than kinetic energy it started with? No. That would violate conservation of energy. But on the other hand, I followed it up with, could 100% of the kinetic energy hit this and convert it into heat? And the answer was still no. Why? Because when we add in conservation of momentum, then it has to be moving, which is some kinetic energy, which then ties back to our conservation of energy, saying we can't convert all the kinetic energy into heat on a frictionless surface. So when we have both principles together, both conservation of energy and conservation of momentum, we have certain things that can and cannot happen. And that's what I'm trying to say here in this first hour, that we have both principles going on here. We have the first law, which tells us things that can and cannot happen based on the energy, but we have also the second law, which tells us things that can and cannot happen based upon entropy. And so that is this new idea. What is the second law of thermodynamics? What is this thing I keep referring to as entropy? And I did mention then, the whole reason we have to have a work less than 100% is because we do have to take some heat out, because entropy is only associated with the thermodynamics. It's the whole reason you never heard the word entropy when we did Physics 121. It never came into question. Something moving has no entropy. It lifts up something else. It has no entropy. It's not a discussion about the entropy there. The thermodynamics is a discussion of the entropy. And therefore, to get the entropy out, we must have heat out. If we have a heat out, the first law says then that number can't be as big as that number. Exactly. And so we learn when we put the two together that the work must be less than the heat coming out. We had this equation on the board where we said let's define the efficiency then as how much work do you get out compared to how much heat you put in. Do you get half of it out? Do you get 90% of it out? Do you only get 10% of it out? Well, when we applied conservation of energy here, oh, whoops, I bumped this. You still hear me, David? Okay. All right. Yeah, double check because I just pulled it up. Okay, good. But the equation here reduces to that. And so now we can say how efficient is our engine based upon its energy. And then these things got to be connected by a certain pattern because of the entropy. And then again, there's our second law of thermodynamics. What really is our entropy? And now that we see this engine going, I just remembered that I was going to start the second one because this class didn't get to see this thing really operate. And so we left last time, but the principle is still the same, that what happens is one side is hot. Now in this model, the hot side is the room and the cold side is the ice that it sits on. In this model, the hot side is going to be this metal piece right here. That's why I'm going to make a little fire underneath it. The cold side is on this side. You can see some cooling fins in between. And so here's hot, here's cold. And the molecules are in here that then push this. Well, I guess it's pushing this piston like in that picture. This is pushing this piston back and forth. And then that turns a displacer which moves the molecules either close to the cold side or close to the hot side. And so this we should see some motion here if I make this side hot. And I know last time we got a little cross breeze and it wasn't really heating the hot side. I don't think we really have that problem because we don't have those other doors open, but I'm going to close that door just at least for a little bit and make sure that that's getting pretty hot. That looks like it'll do it. So remind me about a minute to check on it and see if it is actually starting to make it turn or or not. But meanwhile, as that keeps going, I will, oops, I lost my pen. I will keep talking about this whole idea of entropy. Because like I said, this first 45 minutes to an hour, I want you to kind of get that gut feeling for it. And I think the best way to start with this is maybe just give you the equation. What is the equation for the change in entropy? Now again, I'm hoping that my little examples coming back to Physics 121 and our mechanics help, because when we did our second principle, momentum, what was momentum? Mass times velocity, right? It was two things we already dealt with. You're going to see the same thing here. Entropy is two things we already dealt with. The entropy is the change in energy that flows into your system at that given temperature. Okay. Two things we've already dealt with, right? Temperature and heat. But let's look at this equation a little bit. Let's see what it is saying. Let's see if we can give us some insight. Because again, momentum is, I think, kind of like entropy in the sense that it's made out of two things, mass and velocity. And you can look at them separately, but you really, to understand momentum, you've got to think of them collectively, together, mass and speed. And likewise with entropy. For entropy to make sense, you have to think not only of heat, but heat at what temperature. And it's not just heat, although I should say heat, but it's added energy. Doesn't this kind of look like a fraction? And that's where I want to draw your attention to first. Isn't this really kind of saying how much energy are you adding compared to what you already have? It's like a fractional change. It is saying, look, I'm going to add and increase the energy. I'm going to label entropy really as how much am I increasing the energy compared to what I already have. It's a percentage change. Which kind of opens the door then to get a bigger picture of entropy is kind of a measure of a randomness. Your book uses the word a measure of disorder. It is saying, how is the energy spread out into your system? How much have you increased it by? And of course, what makes it really kind of interesting and challenging is the change in entropy doesn't depend on just one factor. It doesn't just depend upon energy. Just like momentum. Momentum does not just depend. Not quite warm enough. Oh, I spin it the wrong way. Yay, now it's warm enough. Okay, good. And there's my little Stirling engine. But just like entropy depends on two factors, bummer. I did notice it stopped when the flame was over here for a little bit. Oh, now the flame's over here. Good. Ah, good. I don't know what it is, but something about external combustion is just so much more exciting than internal combustion. I mean, just to see something burning on the outside, hot, making something move, just that and that. And I think that's why people into trains really like steam engines, because you know they got moving parts on the outside. You take a diesel electric engine and you don't see anything. It just goes down the tracks. You know, it's not quite as exciting. Anyways, but this is our thermodynamics. This is our heat engine here. And what I was trying to say is trying to give you some insight into entropy, that it's a measure of this randomness. Uh-oh, stopped again, huh? Flame keeps blowing around. Well, what you don't know is the, maybe I need to put up, this used to have a little cap to keep the flame in the center, and we lost it. So now I just fill it with alcohol, and then the flame is all over the place. But if the flame is in the right spot, it should heat the metal. And this one's got, unfortunately, a lot of friction, and we've got to stay hot. Well, you saw it. I'll leave it there. But what I'm trying to get across to you is this idea of entropy is kind of a measurement of its randomness. It's how the energy is spread out. And so what I started to say here is, look at this for a moment. If you are putting energy in, this side is hot, meaning the temperature here is higher, which is great because as it comes out on the cold side, what would you say about the temperature over here? It's colder, right? Now, to get the same entropy coming in that goes out, do you have to have the same amount of heat go in as goes out? You don't, right? It's the same fraction, the same percentage. I mean, if this number came out to be a 3, then when you have something at a lower temperature, you can have less energy. That's why we can put heat energy in, which has a certain amount of entropy. When energy comes out, that energy that can come out can be less than the heat that went in because the temperature is lower. And yet still give us the same entropy. And whatever then energy is left over is the stuff that can go to work. That's why we can still have the first law and the second law still work for us because the entropy is raised on that temperature. And so as long as we have a temperature difference, and that's the key to any heat engine, you can't have the same temperature of them. You have to have one higher than the other. It is the second law of thermodynamics that begins to tell us that the key to this is you take something that's a little bit warmer. That means you can add more energy than you have to take out to get the same entropy. And that extra difference can be done as work. So the bigger we make that temperature difference between hot and cold, the more efficient this engine can get. The closer they get together, the less efficient that engine is. This engine is room temperature, about 20 degrees, and ice, about 0 degrees. It's only about 20 degrees. It's not that efficient. In fact, this one I will take off and let it slow down over the course of the class. But if you want to have fun after class, hold this in your hand. It can operate on the heat of your hand. And so your hand is the warm object, and the room is the cold object. It's not very efficient at all, but you know, that's this whole idea of the entropy. We should be able to calculate what the efficiency is, and that's what the second law will give us. So I'll keep going with my little piece of analogy. Let's go back to this. See this aluminum block? I asked you last time, could that block jump up and hit the ceiling? And you guys all laughed. No, of course it couldn't. Why not? I said. And most of you said at first, well, it doesn't have the energy. And I said, oh, really? Do you remember that calculation? Didn't we find out that there is more than enough energy in there in terms of heat? And if I remember right, didn't we say that if this block cooled down by 0.03 of a degree, that would be more than enough energy to make it go up to there? And yet, you're still telling me it won't go up to there. And I'm going to ask you again, why? Why won't it go up there? So it's not a first law. It's not that there's not enough energy. It's really the second law. And some of you started to see it already. Look, what's going on in those molecules? If you could see all those molecules, what are they doing? They're bouncing around. Aren't some of them going up and some of them going down and some of them are going left and some of them are going right and some of them are going forward? If you got them all to go up, then what would happen to that block? It would go up. So again, it's not that there's not enough energy in there. It's just that they are random. Entropy. If they were all organized, wouldn't it just shoot up? In fact, right now, most of these atoms are going about 500 meters a second in the room. If you had all of those going straight up, this thing would not only go to the ceiling, it would go, I don't know how high that would go, but that would be an extremely high height. So I ask again, how come it doesn't go up there? And it's what we're going to call entropy. There is nothing other than just statistical luck, or bad luck, if you want to call it this, making it go up. I mean, how come I never win the lottery? Every week I pay $1. It's my turn, right? I should win the lotto. Oh, I know. I'm not winning it because the game's rigged. I know those evil people in Sacramento. They're picking those people they want to win. Is there really somebody out there stopping me from winning? No. But I'm not winning, and I probably never will. Why not? Statistics. Those are just the chances of it. And that is probably the best thing I can say about entropy and the second law of thermodynamics. There is not an additional force saying, hey, you can't go up there. There's not somebody putting their hand on it like this big evil devil up here going, oh, nope, not going to let you go up. There's not additional, it's just statistical luck. Let's try some statistical luck or some statistical bad luck. Let's work with this. This right here, let's think of these molecules ricocheting around. Let me draw one molecule or one atom. Let me draw a circle around it. You see that atom? Bouncing around? What would you define as up? Maybe plus or minus 30 degrees? So any motion that is within maybe a cone of 60 degrees would call that up? All right, let's do that. Let's keep it simple. Let's just say, here is my cone going up. Here is 60 degrees. Oh, what are the chances then of this molecule, one molecule, atom, going up? 1/6, right? It's a sixth of a circle. So, okay, I would say the chances of that one molecule going up are 1 in 6. And so if I were to watch it ricochet around, the first time it would hit, the second, the third, the fourth, sometime within about 6 hits, it should be going up. What about the second molecule? What about the one right next to it? Here's a molecule. 60 degrees. What are the chances of that one going up? 1/6. What are the chances of both of these going up?
136.
6 times 6, right? And so for both of them, it's only 1 in 36. Ooh, so I'd have to wait around for them to hit 36 times before both of them went up. Okay, but it can happen, right? How about a third one? And I think you're seeing the idea now. If I took a third one, what's the chances of that one going up? Well, by itself, it's 1 in 6, but all 3 of them going up. Wouldn't this be 1/6 cubed? How about 100 atoms? What are the chances of 100 atoms going up? Now, we're not even close to the total number of atoms in there, but maybe it's worth stopping and at least calculating that one. What is 1/6 raised to a power of 100? 1 divided by 6 raised to a power of 100 equals my chances of getting 100 of them are not quite 0, but I'm not sure I should call it anything but 0. Now, in reality, I have a lot more atoms than this. We said last time this is about 90 grams. So, if I take 90 grams and I divide it by the molar mass of aluminum, which is about 27 grams per mole, I get 90 divided by 27. That is 3.33 moles. How many atoms is that? Well, a mole, 6.02 times 10 to the 23rd. This is about 2 times 10 to the 24th. So that is how many atoms. So what are the chances of all these atoms going up? So I ask it again, is there anything stopping all of them from going up? No, there's not an additional force, but there is a highly, highly, highly unlikelihood that all of these are going to go up. If I tried to calculate this, I would go 1/6, and I would have, wow, 2 times 10 to the 24th. If I try to put this in my calculator, it'll probably break. I mean, 1 divided by 6 raised to a power of 2 times 10 to the 24th gives me 0. It is smaller than my calculator can calculate. I mean, at 100, I almost got there already. My calculator only goes to 10 to the minus 99. This is much greater than that, and so I hopefully am trying to get across to you what I mean by entropy. Why would I say that won't jump up? Statistical probabilities. And I would say it's just not going to happen. Now, wait a minute. You may say, wait. Don't the molecules hit and realign themselves every time? In fact, these molecules hit about 10 trillion times every second. Okay, so maybe the first time you don't get them all going up, but then they're going to hit, and they're going to do this 10 trillion times every second. So maybe within a second they'll all line up, right? So if I take this many atoms and I multiply it by 10 trillion times, that might go up, right? Now, that too is probably going to be a pretty small number. I can even prove that by experiment. Did it jump up within 1 second? Oh, I just didn't wait long enough. Let's wait a minute. How about an hour? Here's a minute. That's not long enough. How about an hour? How about a day? How about a year? How about the entire time of the known universe? What are the chances that this is going to jump up if I sit there and wait for the entire length of the universe? I'm not even going to bother to put it in. 0. It's not even close. In fact, why don't we come back over to here? What are the chances of getting just 100 atoms to go straight up? To do that, I would change this to 100, which now you'll see a number that's not 0, but pathetically small. And it just takes 100 atoms, and they just won't go up. And so if I take 1/6, and I raise it to a power of, 1/6, and I raise it to a power of 100, and I take that number, which we got earlier, there it is, and I multiply it by the fact that there are 10 trillion collisions every second. I multiply that by 60 seconds in a minute, and 60 minutes in an hour, and 24 hours in a day, and 365 days in a year, and 3.7 billion years in the time of our galaxy, our universe. I get the chances of 100 atoms, 6.6 times 10 to the minus 48. Not going to happen. It's just not going to happen. And so my point is this. Yeah, wait longer, right? All right. And that's only 100 atoms, right? And so here's my point about entropy, and why, I think it is the hardest of all of the physical principles we've done so far. It's not an additional force. It's not an additional energy. It's not something I can just really point to. We say it can or cannot happen because of statistics. It would be like me telling you, I'm sorry, you're not going to win the lottery. Well, somebody's got to win it. Sure, yeah, one of these atoms got to go up. But statistically, it's just not going to happen. Yeah, you're far more likely to get hit by lightning. I hope that doesn't happen to you either. But you're probably not going to get hit by lightning, and you're not going to win the lotto. This is just a too small of number. Well, let me try this one. Sometimes I feel like the whole idea of entropy doesn't get across to students because the numbers are so big. So I'll just try pennies. Okay? I've got 6 pennies. I put 6 pennies in my hand, I shake them, and I ask you, will they all come out heads? No.
Chance.
Somebody stopping me? Wait, you say no, and then you tell me nobody's stopping me. So I could get all heads, right? And you got the idea. It's statistics. Nothing is stopping me from getting all heads other than it's highly, highly unlikely. I mean, if I drop this down, let's see what I get. I get tails, heads, tails, 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 heads. All right, so I get 4 tails and 2 heads. So, no, I didn't get all heads. All right. What I get now? Heads, heads, tails, 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 heads. So 3 and 3. Tails, 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 heads, heads. I'm going to get it. Heads, 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 tails. Heads, 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 oh, tails. Oh, darn, that was close. Tails, tails, heads, 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 heads. All right, I think you're getting the idea. Nothing stopping me. It may actually happen. These are smaller numbers. What are the chances that I would get all heads? Well, the chance of getting heads or tails, right, is 2 options, 1/2. And so I would say that if I took 1/2 and I have 6 pennies, there is a 1 in 64 chance of getting a particular pattern. All right? If you remember from your statistics class, your little Pascal triangle, this represents throwing 2 pennies, 3 pennies, 4 pennies, 5 pennies, and eventually 6 pennies. And so what this means with 6 pennies is there is a total here of 64 combinations. The first one is all heads. There's a 1 in 64 chance of getting a heads. So I don't know how many times I threw them, what, about 5 times? I still haven't gotten all heads. But again, there's nothing stopping me. Heads, tails, tails, heads, tails, tails. But I would think that after 64 times, maybe I would get it. I might get it before 64 times. It's just random luck. Heads, heads, tails, tails, heads, heads. Heads, 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 tails. Tails, tails, heads, tails, tails. All right. So I may get it. I may not. There's nothing stopping it. Again, it's just statistical chance. And in fact, if you kind of paid a close attention, what was the most common pattern I was getting? Yeah, I got a lot of 3 heads and 3 tails. I also even got a lot of 4 heads or 4 tails, and then 2 of the other, right? Because that's what this meant. What are the chances of getting 3 heads and 3 tails? There's 20 different ways that I could get a list of 3 heads and 3 tails. I'll list a couple of them. It could go something like this. Heads, 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 tails, tails, tails. The first one could be heads, the next one could be tails, the next one could be heads, the next one could be tails, the next one could be heads, the next one could be tails. It could have gone tails, tails, heads, heads, tails, heads. But you list all these, there are 20 different combinations you could get out of all 64 combinations, and so that's why, guess what showed up the most? What is the most likely scenario? 3 heads and 3 tails. Now, the 4 is not far off, but those together, far in a way, are the majority of likelihoods that we'll get there. And I only have 6 pennies. What if I had 1,000 pennies? What do you think the chances are of me taking 1,000 pennies, throwing them on the ground, and getting 1,000 heads? It's pretty slim, right? Wouldn't it be 1/2 to 1,000 power? Well, what if I did it every second? For a minute? For an hour? For a day? For a year? For the life of the universe? What are the chances of me getting all heads? Or in that case. So 1/2 raised to a power of 1,000. Hopefully that won't be too big. I get a 0. Times 60. Times 60. I'm just going to get a bunch of zeros. Bummer. All right. How about 100 pennies? maybe over the life of the universe I can get at least 100 pennies to land all heads. If I throw them every second for the life of the universe. So 1/2 raised to a power of 100 times 60 times 60 times 24 times 360 times 13.7 billion years. And my chances of getting 100 pennies to come out all heads after throwing them every second for the life of the universe is 10 to the minus 13th. Less than a tenth of a trillionth chance after I've been throwing them every second for the life of the universe. Do you see the idea here of the entropy then? Entropy is an accounting game. It is just a statistical random chance of what are the chances. And so since our numbers and the number of molecules are so large compared to even the number of collisions and the number of seconds in the universe, it's just not going to happen. It's just not likely. And so don't count on it happening. Just like you, I'm sure nobody is counting on winning the lottery. You are here to get an education because you know that you need an income, and it's not going to happen by winning the lottery. You are after other more likely approaches and better approaches. And that's what I'm trying to say here. And so this first, I said 45 minutes and we're a little better than that. I wanted to kind of give you that instinctive gut feeling about what is entropy, because that is our second law of thermodynamics. Here's what we like to say. We like to say then that if the world is kind of left to its own and things start to happen, and so maybe I come over here and I do something, I spin this, I drop this, what happens next is something that is going to be more probable, more likely, more random and disordered, higher entropy than what we started before. At best, it will remain the same. Here's what I mean by that. Let's go back to these pennies. If I take these pennies and I have them in a certain configuration, and although I have thrown them a bunch of times and not gotten all heads, what I will do is start with them with all heads. Hey, they're ordered. Isn't that a lowered entropy? But how did I order them? I did work on it, right? My muscles got hot. The molecules are now moving around in my hand. So they are more disordered. Now this is more ordered, but this is more disordered. And that's the second law of thermodynamics. That as we look at things, some things could get more ordered, yes. But other things in the process will have to do work on it and create a disorder. And the total disorder will be at best the same and probably even a little bit more. Because again, statistical chances. For example, if I start with all these, if I drop a penny, at best, I'm going to have all heads again. Tails. Bummer. And so now I have a more random situation. I can drop that one. Tails too. And so now, again, I have a more random situation. I can drop that one. Tails. And so I have 3 heads and 3 tails. I can drop that one. Tails there too. I can drop that one. Heads. I can drop that one. Another head. And so after I've done all this, right, these pennies now are certainly more random than what I started with. And even if they were more organized than what I started with, like when they're unorganized here and I pick them up, something else in the process, which in this case is my hand, forcing them to turn them over, to do some work, is adding to the randomness. And so the main point here, and what I want to spend the balance of time here, is to say, here is the second law of thermodynamics. The second law of thermodynamics says there will be changes of entropy. As we do things, the entropy will increase or decrease there and there and there. Energy can go into our heat engine and the entropy would increase. Energy would also come out. It would therefore decrease. But when you added all those together, when you take the sum of all the changes of the entropy, you will get, at best, you will get 0. But chances are you may get even an increase. And that's the law, the second law of thermodynamics. It simply says this, that if the process that you are describing, such as, here is the block, without touching it, it's going to jump up to there. If that process is more disorganized, has more entropy, then it could happen. But as you are seeing, for this to spontaneously jump up requires the molecules to all act together going up, or at least a couple hundred of them, and the statistical chances of that are too small, so we say it will not happen. Now, on the other hand, we might say, there are other ways it could hit the ceiling. Could I pick it with my hand and throw it? Is it possible to hit the ceiling that way? Yes. Because in that case, even though these molecules now are going up, the random motion A is still the same. And then B, when I did this, I created heat in my muscles, and the molecules in there are in a random state. And so even though this went up to there, even though those molecules had some organized motion to them, the disorganization in these molecules is greater than the organization that I have given them, and the total increase in disorganization has occurred. And so again, there's no set forces that are saying, oh, this can or cannot happen. What we want to do is look at and calculate the process and say, what's going on? And then from there we can say, will this or will this not happen? Yeah.
Could you say then that the entropy of the whole universe is like increasing?
Yes, so the entropy of the whole universe is at best staying the same, and most likely just getting worse and worse and worse. Well, I'd say it gets more disorganized. Let's take the sun, for example. The sun is this really, really hot ball, molecules moving real fast. Some of that energy is converted into light. Later on we'll call these photons. What happens to them? They go out. That energy gets spread out in a bigger picture. And so we would say the entropy is increasing. The light leaves the sun because the entropy is increasing. It's further out. The energy is spread out. And so as all these stars, these, what we said last time, 10 to the 22 billion stars that are in our universe, as they send the light out, they are increasing the entropy of the universe. Yeah, definitely. Yeah. Thought I saw another question. Let's try a simple case we talked about last time also. Let me clear the board off here, and maybe you can see this idea of the second law of thermodynamics in action. If you recall, last class, and it was too bad we had to kind of cut it in the middle, I did this. I said, let's take a block of aluminum, let's put it next to a block of brass. And I said, if we did that, which the aluminum at 90 grams and the brass at 270, we said, could heat flow from the hot one? We said the aluminum would be the hot one and the brass would be the cool one. Could the energy flow from the aluminum to the brass? Could the aluminum cool down and the brass warm up? Do you remember that discussion? And I broke it into pieces. I said, could the aluminum cool down without the brass warming up if there was nothing else touching it? And we said no to that. Why did we say no? Well, we said no because of the first law of thermodynamics. We said, well, no, that would violate conservation of energy. When we did a calculation, we found out that if this thing, cooled down 10 degrees down to 90, then if you remember that calculation, and I guess I'm wondering too, we got 7.7, anybody remember? 7.7? Yeah. We said that that energy that had to come out of that piece of aluminum would have to go to the piece of brass. So the only way the aluminum could cool down 10 degrees is if at the same time the brass warmed up 7.7 degrees. It wouldn't work for anything else. The brass cannot warm up more or less than that. Otherwise, we would violate conservation of energy, right? And then I said, okay, what about this scenario? What about a scenario where the brass cools down 7.7 degrees and the aluminum warms up 10 degrees? Can that happen? And you guys told me no, but then I pressed you and said, well, why would you say no? Isn't the energy coming out of the brass equal to the energy going into the aluminum? It is, isn't it? So why can't it happen?
It's more organized.
Yeah, it's unlikely to happen. We can see that on a molecular level. We can calculate it from the second law. The reason for it's unlikely is, remember, the hot ones, the molecules are going fast. The cold one, they're going slow. When you put a fast one next to a slow one, the chances of the fast one coming along and hitting the slow one are more likely than the slow one hitting the fast one in such a way that the fast one now goes faster and the slow one goes slower. In fact, think about that. How could that even happen? How could something going back and forth really fast and something going back and forth kind of slow, could it even go slower? And I suppose it might. There is a small chance that what could happen is this fast-moving one stretches all the way out and getting ready to turn back, so it's really going slow at that point. And that the slow one just happens to be going out, and so it kind of gives it a little kick. And so not only is this one stretched out and come to a stop and then gives it a kick, so this one goes real fast. Okay, so there's a chance. How likely? I mean, everything's got to be just right, right? So it's not going to happen. And that's what we mean by entropy. The second law of thermodynamics will forbid this. And that's what I'm getting at. And so our argument was last time, and it is today more thoroughly about random chances, is that this right here is just too unlikely to happen. There is nothing forcing it from not to happen other than statistically it is unlikely. You'll see that in the entropy here. Watch. Let's do both of these calculations. When I look at this one, what would be the change of entropy of the aluminum? Change of entropy of the aluminum. Okay, well, up here I would say a little bit of energy came out of the aluminum. So that is a dQ over T. Now, let's just say at the moment it's a small amount of energy. So the temperature is at 100 degrees and a small amount of energy comes out. Compare that to this scenario. This scenario is saying a little bit of energy comes in divided by its temperature. All right, now coming out. Out. What sign do we give heat when it comes out? Negative. Right? And so I would say right now that this aluminum piece is losing a little bit of entropy. And doesn't that kind of make sense? It's cooling down, it's slowing down. So the aluminum by itself is decreasing in entropy in this example. However, what is happening to the change of entropy of the brass? It's gaining that same amount of energy. And so in terms of sign, plus or minus, would the change in entropy of the brass be plus or minus? It's plus. So again, hopefully this is beginning to make sense here with the entropy, that this one is losing entropy and this one is gaining entropy. It makes sense. This one is slowing down. These molecules, you might say, are more organized. But these are speeding up. So they are more disorganized. So there's an increase to the brass. There's a decrease to the aluminum. Let's add them together. What's the total change of entropy of these two? Are these the same numbers? No. The Q is, right? That's our conservation of energy. But what do you notice about the temperature? Isn't the aluminum at a higher temperature? So this number, which is negative, is smaller than this number, which is positive. So when you add them together, what are you going to get? You get a Q 1 over L, and maybe I should put absolute value, because coming out of the aluminum is a negative, going into the brass is a positive, and hopefully, as you just saw, the fact that the brass is at a lower temperature means that it will gain more entropy than the aluminum lost. So the total change is what? There it is. Greater than 0. The second law of thermodynamics would tell me this is possible. You put a hot object next to a cold object, could the hot one cool down and the cold one warm up? Yeah, because the entropy would increase. That's okay. It's a more random situation. That's okay. Second law of thermodynamics says that's good. Hot object cooling down, cold object warming up. But what does the second law tell me about this scenario? When I do the total there, and I say it's the change of entropy for the aluminum and the change of entropy for the brass, in this case, I would have a dq over the temperature of the aluminum, and when I add it to a dq over the temperature of the brass, but this time the energy flows the other direction, we would be saying the energy goes into the aluminum is getting hotter, that would be a positive number, and so that would become 1 over the temperature of aluminum. Whereas the brass would be losing the energy, so it would be a negative over here, and that number would be, of course, a bigger negative. Can I say that? Bigger negative? Does that make sense? Don't tell your math teacher, but bigger negative, right? That is more negative than that is positive, and so this is saying I get a number less than 0. Can that happen? No. And that's my point. This entropy is a way of calculating the randomness. Anything that increases the randomness means this is more probable, more likely. It could happen. But anything where the randomness is less, anything where the entropy decreases, that can't happen. And so there's our answer to how come the energy can go from the hot to the cold, but it can't go from the cold to the hot. And so I bet every time in your lifetime you have seen this, no questions asked. Hot cookies out of the oven, cold room, before you know it, cold cookies. I doubt if you've ever hot cookies out of the oven and they just get hotter. They sit on the kitchen counter. It just doesn't happen. Even if you waited for the entire length of the known age of the universe, it's just not going to happen. So again, that's what we mean by entropy. Entropy is a statistical one, and it's one more feature that we have to throw in when we say what can and cannot happen. We have to look at the energy, but even when we have a case like this where the energy is conserved, still things may not happen. We have to look also at the second law of thermodynamics to decide what can and cannot happen. So, in the hour that we have left, let me say this. Good news, we've talked about all the physics. Let's start putting it all together. There's no more physics you're going to learn this semester in thermodynamics. So if you've enjoyed this stuff, you're probably going to go home and cry. No, this was just getting good. I wish we had another chapter. I do too, by the way. But if you're not liking the thermodynamics, you're going to be glad. And, you know, in fact, you probably think we should just take the test this Tuesday. Why wait until after spring? No, you're not thinking that, right? All right. But what I would like to do is start to do some examples now. I'll do examples out of the book on Tuesday, but for today, let's look at some of the processes they have in here. Watch. A really good one to discuss here at the beginning is the internal combustion engine, the four-stroke engine. Let's bring this one back up. You probably remember seeing, we talked a little bit about this one, how does the engine in your car work? The four-stroke internal combustion engine. And it, again, running through this real quickly, it works something like this. I'll wait until it comes up to, say, fuel goes out. Here's kind of the beginning, if you will. It opens, fresh oxygen and fuel come in, it gets compressed, spark plug ignites it, makes it real hot, forces it down, valve opens, exhaust gas go away, we start all over again. So up and down, 4 strokes, down, 1, up, 2, down, 3, up, 4. We call it a 4-stroke engine. We've got places where, like right here, the air comes in, intake stroke. They close, they compress it, called the compression stroke. We burn the hot gas, we push the car forward, power stroke. We exhaust the gas out the tailpipes before we bring in new fuel. So we've got our exhaust stroke. If I were to study this from a thermodynamics point of view, what would it look like? And so, clearing up the board here, let's look at the energies, let's look at the efficiencies, let's look at the entropy. What is going on in my internal combustion engine? And hopefully then, when I understand what's going on in my internal combustion engine, I can develop better engines. I can become rich and famous. I can remember my humble beginning at the community colleges and donate money back to fix our leaky ceilings and our broken tile floor, and a professor who likes his Ferraris red. Right? And so what goes on is an important discussion in the thermodynamics here. So here's what I'm going to do. I'm going to put a PV diagram. And I'm going to then look at these 4 strokes and see if I can describe on a PV diagram as well as mathematically what is going on. Why don't we begin at, and it's a cycle so it's hard to say where to begin, but I'm going to begin at the intake stroke. So right there, that valve opens, the piston is up at the top, and so if I was looking at a PV diagram, I would say we're probably at atmospheric pressure right now, right? The valve opens and it's going to go in, or we're at whatever pressure happens to be if the air on the intake is compressed, which, you know, you may design an engine that way too. But the point is the valve is open, and whatever the pressure is for that intake valve, that's going to be what's in the cylinder. And not only that, we are at what your author calls a small volume. He calls it volume number 2. I'm not sure why he picks volume 2 there, but I'll call that volume number 2. That's the smaller one. Okay, now watch what happens. So, let me get back over here. So here we come, here's the exhaust. And so, valve opens and the piston goes down. But notice the valve's open as it goes down, which it should be, of course. You're trying to get fuel and oxygen into there so you can combust it. What would that look like on a PV diagram? Yeah, and so if I start here, I would be an isobaric process is what we would say on our PV diagram. And I would keep going until I got to the bottom of the movement of that piston. And so maybe I'll just put here intake to kind of remind me in my notes here that, okay, that is the part of the piston going down, bringing in fresh oxygen. Okay, so then what happens? Well, then the valve closed. We're not quite there yet. Here we go. Here it opens. Now watch, valve close, and we compress it. What kind of process is that? Would it be constant volume? No. Right? It's getting compressed. Okay. Would it be constant pressure? No, valve closed. This engine's going pretty fast. 4,000 RPMs. Yeah, so I'm probably going to go with the adiabatic here. Perfectly adiabatic, probably not, because the engine is made out of metal and the heat transfer is pretty good to the metal walls. But over idealized, the best one I could call it would be adiabatic. And so I will say it looks like that. In fact, your author calls this point A and this point B. And so that's the adiabatic. I'll put here compression stroke. So that's the compression stroke. And of course the volume goes all the way down until it gets to the top again. But then what happens when it gets to that top? It ignites, right? And then the gas burns. Let's just say that happens real fast. I mean, fast enough that the piston barely got a chance to move. So what would we be saying why the fuel was burning? Pressure's increasing, temperature's increasing. What kind of process? Yeah, I would call it probably isovolumetric at this one, because again, without too much change in the volume here, this burns pretty quickly. Let me draw a line then that is straight up. Call that C. In fact, let me put a little arrowhead and call this is the burn. This is what we would call Q sub H. This is where the energy is added into the system here. This is eventually where we get energy, right? It comes in because we have burned the gasoline. And so there's the adding of energy right there. We have our burn. Now, right after the burn, what happens? Yeah, it's expanding, right? It's pushing the piston down. That's what we call up here. Here it comes. Oh, next one. The power stroke. So it comes up. Here it compresses. Gas burns right there, and now pushing it down. That's the main operation of the engine. That is the part where it goes down and has an adiabatic part to it. This is what I'd call the power stroke. Then again, it happens pretty quick, so I'll call it adiabatic. But again, I don't think we could say it's exactly adiabatic. We know our engines get hot. That's why we have them water cooled and all those good things here. So it's a little bit extreme to say it's adiabatic, but it's a good place to start. So I'm going to say it's adiabatic. Then what happens? Once it goes all the way down to the bottom, right there, what happens? Yeah, the valve opens again before the piston starts to go up. Now, before the piston starts to go up, what would happen to the valve? What does opening the valve do? Yeah, it drops the pressure, doesn't it? And so I would say very quickly the pressure dropped. You might even say that's where the heat comes out, although to be quite honest, the heat would come out not only when you open it do some of the molecules go out, but then what happens next after you open the valve? Yeah, then the piston rises back up right here. Here we go. Here's the power. Valve opens, there's a drop in pressure. Then the exhaust stroke goes up, squeezing the gas out at a constant pressure. And so I guess I would call that then the exhaust stroke here. And so we'd be leaving there. Did you have a question, David? Or?
No.
Oh, okay. All right, so is that a fair PV diagram? And of course, if I can get nothing else across to you today, notice this, that I can calculate all these great pieces of information. What's the efficiency of the engine? How much work does it do? How much does it warm up? What's the entropy? All these things we've been talking for the last 4 chapters, they're all buried in that PV diagram here. And so maybe a good place to start is this question about what is the efficiency of this engine? Maybe I should begin with this. Will it be 100%? No, why not? Yeah. Or maybe I should even start further back. Will I get more kinetic energy out of this engine than heat I burned? No, why not? Conservation of energy, first law of thermodynamics. Okay, fair enough. Will I get an equal amount of kinetic energy out of this compared to the heat I put in? No. Why not? Second law of thermodynamics, right, the entropy issue. So you guys got it. So I would expect the entropy to be less than 100%. In fact, well, on the next engine we'll do, we should probably ask this question. Since we just said you can't have an engine that's 100%, maybe we should ask what is the most efficient we could have. Because we may not be able to make an engine that is 100% efficiency because of the second law of thermodynamics, but that shouldn't stop us from trying to figure out what the most efficient is that we could, and then see how close we can get to that. And so this engine is not at all the maximum efficiency. It's not bad though, but it's not the maximum. It's got some other engineering problems, so even at its efficiency, its maximum efficiency is not really what we get. I mean, my car only gets like 30 miles to the gallon. Even a good car getting 40, 45, and they're still not close to what the maximum they could get. They've got a lot of improvement. But all of them use this kind of cycle, and it doesn't it comes kind of close to the maximum. But we should talk about that, what the maximum is. Because again, as you guys become engineers, you would never strive to get 100% efficiency. That would make no sense. You would say, well, that would violate the second law of thermodynamics. But you should be able to understand the second law of thermodynamics to see what could I get, and therefore keep designing to get as close to that as I possibly can. And so this engine is reasonably close. It has a lot of problems. In fact, maybe I should put here, this was developed by a guy named Otto, a German scientist, and so he did the thermodynamics, whatever year he did this, but he looked at this by the way, Diesel followed behind him and did the Diesel cycle, so I think you got a homework problem on the Diesel cycle there. But he looked at the thermodynamics, and the Diesel cycle is a little more efficient here than the Otto cycle. Maybe you guys are smarter than me. When I was in your seats about a decade ago, or no, a century ago, excuse me, yeah. But notice it is not the Otto cycle. And I just remember my teacher just rattling off the Otto cycle, and 4-stroke engine, and I was like 3 weeks into the class before I realized, oh wait, this Otto is the name of a German scientist. It's not short for automobile. But anyway, so there's what we call the Otto cycle. And you'll have a homework problem on what's called the Diesel cycle. And we'll look at another one, the Carnot cycle, here in a minute. And so there's a lot of different processes. This is the Otto cycle. And so as I started to say, here's my question for you. What is the efficiency of this cycle? If you build an engine this way, and ignore all other frictional effects, and you could take all this energy and somehow get it to the wheels, what would be the efficiency of this engine? And so this is our definition of efficiency. I'll put absolute values here just to keep reminding you that I'm talking about how much work compared to how much heat, and even though the work is coming out, I'm not going to treat it as a negative number, because I'm going to say how much work did it do on my car to make my car go. And as we started this class already, we could replace this with 1 minus QC over QH. And again, I'll just put an absolute value there. And so really this question about how efficient is it really comes down to a calculation of how much energy did I have to put in as heat, and how much did I have to, I'll call waste, to come out. But it's not really waste, it's stuff that I need to come out, because if I don't have that, I would violate the second law of thermodynamics. So I need some heat coming out of there. I wish all the energy could come out and the tailpipe wouldn't be hot, and all that energy would make the car run. But the truth is, I need hot gases coming out my tailpipe. Without hot gases coming out my tailpipe, I don't have entropy. And so that serves a purpose. Unfortunately, it serves a necessary purpose according to the laws of physics. And so I'm going to have a little bit of heat. And that's my calculation. So let's give it a try here. How do you calculate? Give myself enough room. I'll come here. How do I calculate the energy going in, or excuse me, coming out of the engine into the environment when it's cold or hot? What kind of processes are these? What did I draw on the PV diagram? Isovolumetric, right? How do you calculate the heat in an isovolumetric process? Good. N CV delta T. N CV delta T. So in the case of the cold one, it would be NCV, and the cold one is labeled here, and the change in temperature, I should have put a D there. The change in temperature would be the temperature at D minus the temperature at A. And notice, I will put it in the order of the high temperature to the low temperature, so that this will come out to be absolute value, so I can put in absolute value. Because again, heat's coming out, and we've been calling those negative numbers, but I don't want that to be a negative number in my discussion. I want it to be a positive number. Likewise, how do I calculate the heat going in? Well, change in temperature. And so it would be whatever the temperature is at C minus the temperature at D. So minus the temperature at C, excuse me, a hot one. Oh yeah, the hot one is C. And the lower one, which is B. So if I come back over here to my first calculation for efficiency, you can see that I am going to take this ratio, right? How much of the cold over how much of the hot. And these two will cancel off, and I get the temperature at D over the temperature at A divided by the temperature at C over the temperature at B. Okay? Let's keep going. Because that's not all we learned in these last couple of chapters. We learned all kinds of processes. What about the adiabatic? If you look at this process, it has not only your isovolumetric, but it's got two adiabatics. What did we learn about adiabatic? I'll put it here. How is pressure and volume related? Isn't that the mathematical connection we worked out between pressure and volume? Oh, what if I change pressure into temperature? Oh, what if I did this? What if I replace pressure with NR, and maybe I should put 1, 1, 2, 2. But if I replace it with nRT1 over V1, V1 to a gamma, and over pressure, I'll put nRT2 over V2, V2. So I will replace pressure with the ideal gas law. An N and an R show up on both sides. And so I end up with temperature of 1 times volume 1, gamma minus 1, is equal to temperature 2, volume 2, gamma minus 1. And I think at this point, we've done most of our calculations connecting pressure and volume. But after a couple of steps of algebra and the ideal gas law, we see that temperature and volume are also connected. We could even write another equation that would relate temperature and pressure. But this is pressure and volume related. This is temperature and volume related. And we could have pressure and temperature related. But this one will serve me well. So I'll stop there. Because if I take this relationship and I apply it to the adiabatic process, let's look at the power stroke. In the power stroke, it starts at C. So the temperature at C and the volume at C, gamma minus 1, would be the same as the temperature at D times the volume at D, gamma minus 1. Right? That's what we mean by the adiabatic. C and D are connected. I'll take that to the other adiabatic process also. Isn't A and B connected by the adiabatic process? So the temperature at A, let me do B first. It'll look a little nicer when I make the next step. But if I take the temperature at B times the volume at B, gamma minus 1, and then the temperature at A times volume at A, gamma minus 1, that's the adiabatic. So both of these are the adiabatic processes. Let's subtract the two. Let me take C and subtract B. See, that's what I have up here, right? C, subtract B. But before I do that, let's talk a little bit about the volume at C and the volume at B. What is this saying about the volume at C and B? They're the same, right? They're what we call volume number 2 here. And so when I subtract these two, it would be temperature at C minus temperature at B times volume number 2 gamma minus 1. These are the same volumes. And hopefully you'll see the same thing on the other side of the equation. What would I say about volume at A and volume at D? Yeah, they're volume number 1. They are the same here. And so this would become temperature at D minus temperature at A, and then I would have volume number 1, gamma minus 1. If I took another step of algebra here and made it look like that over there, I can divide by temperature at C minus temperature at B and get rid of that. I can also divide by volume at 1 gamma minus 1 and get rid of that. Because see that right there? Temperature at D minus temperature at A over temperature at C minus temperature of B. Isn't that what I have right here in this little equation for the efficiency? So I can replace this as 1 minus volume 2 over volume 1 raised to a power of gamma minus 1. Yes?
Sorry, how'd you get rid of the volume 1 and
Over here?
Yeah.
I divided both sides by gamma minus 1 until they canceled here and showed up over there.
Oh, okay.
And the same thing could be really said about what I did over here. I divided by that, which canceled and showed up over there. Yeah. So a couple steps of algebra. And hopefully not too many, that I didn't lose too many of you, but you know what they like to say, that the more complex we make it, the harder we make it, the more of you drop out and the higher wages go up, right? You know that's the evil plot. It's why we put your physics and math tests on the same week. You don't think this just happened at random, do you? Yeah. Okay, so there is the equation. Let me keep going, though, because your author's going to take one more step. And I'm not sure this makes it look better, but I guess he is. He turns this into a compound fraction. He puts the volume number 2 down below, and he turns a simple fraction into a compound fraction, which is not usually the way you go, but I think I know why. Which one's bigger? Volume 1 versus volume 2. And this is often referred to as the compression ratio. It is referred to when you are designing an engine of saying, how big is this volume when the piston is at what they call bottom dead center compared to top dead center? What is the ratio in them? In fact, last night as I was thinking about this lecture, I was kind of curious. So good thing Google has all the answers. I looked up my car and then my wife's car. Mine had a compression ratio of 9.8. My wife's car was 9.9. I'll take mine and ask, what would be then the efficiency of my engine in this cycle if everything worked right? Now, don't get me wrong. I know that there are other losses of energy, especially as it goes from my engine through my transmission and my powertrain. That transmission gets really hot. There's obviously a lot of energy being wasted there. I mean, it's the whole reason I got transmission fluid flowing around, cooling the whole thing, and then flowing over to my radiator and cooling that. But that aside, what could I expect to do, or what could I do here? And so if I were to take my numbers, I would put 9.8 there for the compression ratio of my engine. What about gamma? It is CP over CV, good. And of course both of those, CP and CV, depending on what kind of gas you have. So what kind of gas do I have? You know, what's inside of this thing? It's a little bit of oxygen, a little bit of gasoline, and mostly nitrogen. right? And so don't forget that. It's worth mentioning here that what's actually pushing your car are these hot nitrogen. I mean, you use the gasoline, sure, and the oxygen to make the energy. But what really the point of that was to make the nitrogen move fast, and the nitrogen is what is pushing on it. And so this is really a diatomic. And you know, it's maybe too bad I need the nitrogen to push the car, because the other component of an internal combustion engine is smog. And smog is usually nitrogens that have mixed with oxygen, and you get these nitric oxides. And so you get it real hot and the nitrogen breaks apart and hooks with some oxygen. If I didn't have any nitrogen in there, I wouldn't have that problem. But if I didn't have any nitrogen, I wouldn't have my car going anywhere. So sure, no smog, no car. Kind of go together here. Of course, we have ways to control it, hopefully, that we don't mix our nitrogen into oxygen. But the point is, it is mostly diatomic in there. And so I am going to put 1.4 minus 1. And that was our ratio CP for CV for diatomic. Because remember, diatomic has 5 degrees of freedom. So CV would be 5/2 R, and CP would be 7/2 R. So let's see what I get. 9.8 raised to a power. 9.8 raised to a power of 0.4. It's about 2.5. And then if I go 1 reciprocal of all that, about 60%. So my car, at best, and I know it's not even close to that, but at best would be 60%. That is 60% of my energy that I burn in my gasoline shows up as kinetic energy, meaning the other 40% needs to be heat. And then I need to have then a radiator to cool it. I need hot gases to come out the tailpipe, and that's just the best I could do with that particular cycle. Now I will tell you, this is not the most efficient cycle. There is going to be some entropy created here, so this isn't bad. And to be quite honest, if my car was getting 60% efficient, I'd be extremely happy. Like I said, I get about 30 miles to the gallon, and I think that gives me like about 30% efficiency. So we're about, my engine is doing about half as well as it could do, and so there's a lot of room for improvement, right? Yeah.
Why does burning nitrous oxide make it so much more powerful?
It burns hotter. Yeah, more violently. Yeah. Yeah. Is it? I was going to say, is there? Well, that's my answer. It's going to burn hotter, make the molecules. It'd be like, why does my bike go faster when I pedal harder? You know, I push harder. That's what's pushing it, is those molecules. There might be more to it than that also, but that's got to be part of it. Anyways, like I said, there's my 60%. Now that we've talked a little bit about energies, how about the entropy here? Well, let's put that into our diagram here. As I come over here and think about this entropy here, let's see. There was certainly this part right here where there must have been a change of entropy. Right? Let me write it this way. What is the change of entropy from B to C? Because that's the point where I'm giving energy to it. I'll ask you guys, will this be a positive number or a negative number? Positive, why? No. It's not because it's always positive. The whole process, right? We can have, like we put the hot and cold. One was positive, one was negative. But we had the stuff that was positive was more positive than the stuff that was negative. So not everything has to be positive, but when we add energy to it, it is positive. So this is a positive. This is making the molecules go faster. Okay. So in a mathematical sense, we can say we've added positive energy, and that's why the entropy goes up. From a conceptual point of view, we could say we're making the molecules go faster. They're racing around. There's a more distribution of the energy of the system, and the entropy has gone up here. And so there is my idea of the entropy. So this should come out to be a positive number. How do I calculate it? Well, you might remember, and maybe I should put it in integral form, that about a half hour ago or so we had this. But what I probably should have emphasized is the temperature may not be constant. And so this is probably better written with our calculus that says a small amount of entropy change would be based upon a small amount of energy added at that temperature. But then you may have a new temperature, so you'd have to integrate that. And so if the temperature is changing as you go along, you have to add it all up until you get the total change here. And that's what I'm going to have here. As we burn the gasoline here starts at a low temperature, or the molecules start at a low temperature. And then as the gasoline burns, those molecules go faster, 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 and the temperature goes up. And so to actually calculate the entropy, I'm going to have to do my calculus. I have to add it up. I have to do an integral. And so this is really an integral of Q over T. That's what I meant to say there. And that's why I wanted to do an example calculation before you guys go off this weekend and you do the homework, and then you'll be ready for the test on Tuesday. No. I can't push you back into the spring break one. No, okay, good. Yeah.
Which T is it?
Well, it's the temperature at that moment. So again, it would be at when you first burn a little bit of gasoline, there's a little bit of energy at a low temperature. Then you burn a little more gasoline, and 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 a little more gasoline. And you keep adding energy, but every time you are adding energy, the temperature is a little bit higher. And so the entropy associated with that energy is a little bit different. That's why I have to do an integral. Fortunately, it's not a hard integral to do. Let's do this. How do you calculate the energy that you add when you are at a isovolumetric process? Here to here. We did this one earlier. Isn't this N CV dt? And so this would come out to be NCV times an integral of dt over t. Yay! Can I do that integral? Or maybe I should ask, can you do that integral? I know I can. Right, it's a natural log. So it's not a hard one, but as you pointed out, the temperature does change. And so we're going to have to do the integral form here. And so it's NCV, and now we would get NL, natural log of, and in my case, I'm going from a temperature at B up to a temperature of C. And so it would be the temperature at C divided by the temperature at B. And so there is my entropy change from B to C. And as you guys already told me, is this a positive number or a negative number? Physics tells me it should be a positive number. Aren't I adding energy to it? I'm making them to go faster. I'm making them more random. What does the math tell me? Anytime a logarithm greater than 1 is a positive number, right? Temperature at C is greater than the temperature at B. So I have a ratio greater than 1. I'm going to take a log of something greater than 1. I am going to get a positive number. So sure enough, there is a change of entropy at this point where I am burning the gasoline. Let's continue. What about the change in entropy from C to D? I'll start off with, what kind of process is it? Adiabatic, right? What does adiabatic tell me? Add no Q. So, 0, right? There's no energy being added during that process. I take an integral of dq over dt. dq is 0. Add up a bunch of zeros. 0, 0, 0, 0. What are you going to get? 0. That's going to be the easiest one you've ever done, right? And that's the change in entropy from C to D. Now, if it helps, think about this conceptually. Especially when you realize that this is an expanding gas, and we learned that it cooled, right? The adiabatic process, when a gas expands, it cools. So you might think, wait a minute, the molecules are going slower. Isn't that less randomness? Shouldn't the entropy go down? Except they spread it out, didn't they? So those molecules were really hot in a small volume. Now it expanded adiabatically. Now they're cold, but they're spread out in a bigger volume. And so the bigger volume is an increase in entropy. The lower temperature is a decrease in entropy. The two together make no change in entropy. And so the adiabatic process is a perfect balance of expanding of the gas and a cooling of the gas, so there is no increase in entropy during that process. I'll keep going. What about the process from D to A? And let me emphasize again, it would still be an integral of Q over T. What kind of process do I have from Q, or from D to A? Yeah, it's really what we did back here in B to C. And so maybe I'll just put the answer all the way over to here. It would be NCV natural log of, and in this case I'm finishing at a temperature of A, and I'm starting at a temperature of D. Both physically and mathematically, is this a positive number or a negative number? Negative. Why? Okay, physically, heat is leaving from this. We are, in a sense, cooling the gas down. We are getting more organized. The molecules are moving at a lower speed. I would expect a decrease in entropy during at least this part of the process. From a physical point of view. Mathematical. Which temperature is bigger? Right? D is, right? Up here is D, and then we open up the valve and let it cool down here. Actually, it's a little more complicated than that. We actually opened up the valve and got rid of molecules, but we overly simplified it and said we're going to get rid of heat. All right, but if we do that, this ratio should be less than 1. What about a natural log of less than 1? Negative, right? So this is positive. The next one is 0. This is negative. And finally, how about the last one? What's the change of entropy as I go from A to B? Yeah, there's another 0 for me, because that, again, is an adiabatic process. There is no change of Q. All right, so there, I guess maybe even a little more formal, a reversible adiabatic process. But there are my 4 processes. So if I asked for what is the total change of the engine, now make sure you caught that. I think we'll have enough time to do the next engine here. But I said of the engine, because there are other things going on. Wouldn't there be a change of entropy from the hot environment in change of entropy in the cold environment? So if I wanted to know the entire change of entropy of everything, now the second law of thermodynamics says if I add all those together, what should happen there? Yeah, it should come out to be greater than 0. Okay? So I'm not going to try to calculate the change of entropy of everything. I'm going to avoid the environment here. But when energy was going in here, and we said the engine was gaining entropy, the world out here was losing entropy. And then when the heat came out and we said the engine is losing entropy, then the world is gaining entropy. And if we were to add all those together, all 4 processes of the engine plus the environment, it will come out to be greater than 0. But I'm not going to go that far yet. In fact, I won't even go that far at all. We'll do that with the other engine. But what I do want you to see is, what about the engine itself? What do you think these 4 should add up to? 0. Why? It's a full cycle, right? We get back where we started. So just like one full cycle, the change in internal energy got to be 0. We got to get back to the same energy. We got to get back to the same entropy. And so I claim that if I add the change of entropy from B to C, from C to D, from D to A, and from A to B, I will get 0. Let me leave these little formulas on the board here. And let's try and calculate all these. Fortunately, 2 of those were already 0, so those aren't real hard to do. But this first one, B to C, was NCV, natural log of the temperature at C over the temperature at B. This one, the C to D, we said was 0. This one, the D to A, is what we got there. So CV natural log of A to D. And I guess really that's kind of my question. Should come out to be 0. Does it? Yeah, it will. Now we got a little bit of work to do, because obviously the C, V, and the N are the same. But what I have is the natural log, and I have 2 natural logs added together. And you already told me one's positive and one's negative, but are they equally positive and equally negative? Well, let's try our adiabatic process again. Remember, TV gamma minus 1 equals TV gamma minus 1. Let's apply that to the power stroke C to D. C, C, D, D. Let's also apply this to the other adiabatic process, B to A. B, B, A, A. Let's divide the two equations and re-remind ourselves, what do you say about the volume at C compared to B? C to B are the same. So temperature at C over temperature at B is what that side reduces to. Same thing here. The volume at A and the volume at D are the same. They can cancel off, and then you get temperature at D over temperature at A. The reason that is helpful then is I can write this as NCV. I've got the natural log of temperature at C over temperature at B. Nice thing about logarithms is when you add our logarithms, isn't that same as multiplying their products together? If you look careful at the first one, C over B, then this becomes NCV, natural log of C over B is D over A. We already have an A over a D. What is D divided by D and A divided by A? So I get a natural log of 1. What is the natural log of 1? 0. Yay, wasn't that fun? Look at all this math we get to do here. So after a bunch of integrals, we can figure out that it is true, that there is some change in entropy. And as we take the time to calculate it, you'll see that in one complete cycle here, the change in entropy is 0. We can come back where we started. Question?
Is that what you said was reversible?
Well, in this case, I would call it reversible, yes, because the engine has gone back to where it started. It's ready for the next cycle. Yeah, and it's real important then when you're building an engine that you develop something that is reversible, because the idea is we make it work once, then we can just keep doing it again and again and again. That's well, those kind of go together. If the change in entropy equals 0, then we can make it keep. If the entropy had not come out to be a change of 0, then we're not getting back to the same place. Yeah, yeah. And we're maybe, can only do it a few times before we, run into troubles here. All right. Well, as I mentioned, and in the 20 minutes we have left here, let's try another cycle. Maybe we can go a little bit faster with this cycle since you kind of get the gist of this. But this cycle here, I hope you got across here that the change of entropy of the whole cycle is 0. And maybe this was your question. I am not saying the change of entropy of the whole universe was 0. Because if we come back over to here, we could say that this temperature was probably warmer than what got put into here. So when we burnt the gas, not all the energy got into there. Therefore, what energy or entropy was gained is not the same as what was lost. And since what was lost was at a higher temperature, that means the entropy change lost is a smaller number because the temperature is on the bottom. And so that means going in is a greater gain than was lost. And so this engine does have an increase of entropy of the whole environment. Same thing can be said here, that as the heat comes out, the cold area is probably colder than the exhaust gas coming out. If you ever touched a tailpipe, you can feel that right away. That, hey, the environment outside is obviously cooler than the tailpipes coming out. But what that would mean in terms of entropy, since it is energy divided by temperature, and this temperature is colder, this one is gaining entropy, the same energy, but at a lower temperature. So this is a positive more than this is a negative. Just like this one over here was more positive than that is negative. So overall we would have something more positive. So overall we would have a increase in entropy of our universe, we like to say. Now, not the engine. The engine is zero, as I tried to just demonstrate. But the whole environment, it is an increase. And it's because of that increase led us to the next cycle. A guy named Carnot said, look, this Carnot cycle is one that the entropy of the entire universe, not just the engine, but the stuff on the outside, is zero. And his argument was, if you could find a cycle that had a change of entropy of zero for everything, not just the engine. I mean, all engines, if they go back to a cycle, their change of entropy has to be zero. I think I got that across. But if I'm saying the change of entropy, not only what's going on in the engine, but also in the environment, if you find that to be zero, that's got to be the most efficient. Because the second law of thermodynamics says that it can be zero or greater. And if it's greater, that means you've kind of wasted energy off to the environment. And so Carnot said, let's look for the most efficient cycle. If I can find a cycle that would make the change in entropy of everything, both the engine and the world around it, zero, then that's the most efficient you can be. You could never be more efficient. There may be other cycles that are just as efficient. And that's kind of actually the fun part of designing engines these days. It's for looking for cycles that are as close to this ideal as possible, or even ones that are just as ideal but operate a little bit different. Because as we'll see here in a second, this engine or this cycle really does not make for a good engine. It has to operate too slowly for it to make a good engine. You've got to let things expand and contract at constant temperature, and to do that it takes time. So again, this cycle probably is not the ideal one to actually build, but it is the ideal one to strive for. What other cycles can we get? And as I pointed out, this one I just erased, the Otto cycle, is not the ideal one. It's not bad, and we use it a lot. It's got a lot of other important reasons we like it, but it is not the ideal one. And so we like to say then, what is the efficiency of the Carnot cycle? And keep this in mind, that the efficiency of the Carnot cycle is the maximum efficiency. So it would be nice to know that one, because we already said from the second law of thermodynamics that we're never going to shoot for 100%. But what should we be shooting for? As you saw my calculation on my car, I calculated with my compression ratio to be 60%. The first step is, could I get the other moving parts in my car to cooperate so that I could get a 60% efficiency? I mean, that would be a good first big step. But if I eventually got to 60%, I might take the next step. How could I change the cycle, what's going on in the engine, to something that's even more efficient? And so the Carnot cycle gives me something to press for, something to shoot for. What could I get? Because I already know, like I said, I can't get 100%. I'd be foolish to shoot for 100%. Despite the fact, if you just do Google and say, hey, find me an engine that's 100% efficient, you'll have all kinds of websites out there. And you too, for $2,000, can be the original investors. And you too will someday make millions. And no, you won't. you'll lose $2,000. Because for that to work, you have to violate the second law of thermodynamics. Now, if you could do that, there's a Nobel Prize right there, because if you could show that one of the laws of physics isn't really a law of physics, that's probably got to be more valuable than the whole discovery and the whole engine thing. I mean, you make $1 billion from the engine, and you make fame and popularity and another $1 billion from all of the Nobel Prizes and stuff there. So, yeah, like I said, it's a huge lack of understanding of the second law of thermodynamics that is out there in the world. Anyways, let's talk about this cycle and then draw our PV diagram here. This cycle has 2 adiabatic and 2 isotherm. I think you were probably watching it here. This is this gas. You can probably kind of model it as this one here that you've seen a number of times. But here's the idea. I'll start at A, but if at A we've compressed it till it gets warm, you put it near a hot object. As you pull it up, or you let it go on its own because it's under high pressure, as it goes up, if it wasn't in contact with this hot bath, so in my case it may look something like this. If I take this air and I squeeze it down and hold it into place and warm it up, that would be a small volume at a high temperature. And so if I release it, but let it up slowly, that first part of the cycle, as it comes up, because I'm doing it slowly, is an isotherm. If it did fast, it'd be adiabatic and the gas would cool. But to keep the gas from cooling, I let it go slowly and heat energy comes out here. And so that first part of the cycle here, the A to B, is an isotherm. Pull it up slowly. Again, that's why this is not going to make a very good engine. I want to pull it up so it doesn't change its temperature. But it's also the main step that Carnot realized this is the one that will make the change of entropy of everything 0. You'll see that in a minute when we get that far here, in 15 minutes here, okay? But that's an important logic here. Of course, after it goes up about part way, he then says take it away and let it continue to expand because it's under pressure, and as it continues to expand, it's going to cool. It will not be an isotherm anymore. It'll be what we call an adiabatic process. And if you let it expand enough, it will cool to another lower bath temperature, which in my case would be ice water. It would have to expand way up here for this to cool to ice water, but that's what they're trying to show. Expand out until it turns blue. Once it turns blue, go ahead and start compressing it again, but slowly. That's the key. Because if I compress it slowly, it stays at the same temperature. That kind of looks like a flat line. I don't want to indicate that. And so there's another isotherm. That's what this one right here, this blue is. And so as you are squeezing it down, if it was adiabatic, it would have warmed up. But that's why it's near the cold bath. So heat would come out. In fact, maybe I should even put a little arrowhead here. This is Q coming out. Over here was Q going in. So during that part was where energy came in from the hot bath. During this part, energy is going out into the cold bath. That's why we do it slow. That's why we leave it next to that bath. That's why, as you'll see, this is why this is going to be the most efficient one. It's that constant temperature that really plays the key role in Carnot's logic here. Of course, eventually then you compress it. You take it away from the cold bath and you compress it. And that's what this last part of the cycle is, which we're kind of far from it now. Here we go. Expand, cooling. Get to the low temperature. Then when we get here is where we bring in the cold bath and we compress it slowly. That's the isotherm. Then when we get here to D, we take it out of the cold bath and compress it adiabatically till it warms up, until it gets as warm as a hot bath again. So 2 adiabatic, 2 isotherms. As you'll see, the change in entropy of everything is 0. Can't get more efficient than this. But let's calculate it. You might remember that we said 1 minus the energy that comes out on the cold side divided by the energy that went in on the hot side. That's why it was kind of important to do these calculations here. Let's calculate those. What is the energy going out on the cold side. And let's start with the question, what kind of process is this? It's isotherm. How do we calculate the heat in an isotherm? Yeah, good. I think this is the harder one, but it comes from this. The change in internal energy is 0 in the isotherm. So the heat is negative of the work. Now in our case, we're just doing absolute values. So let me not worry about the plus or minus sign. But the work then is the integral of P dV. And I won't worry about the minus sign. And the pressure can be written as nRT over V dV. And so when we point out the temperature is the constant, we can get the integral, the temperature out of the integral and get an nRT, and then we get the natural log of volume 2 over volume 1 as we integrate from one volume to another. And so we got the heat calculation from the work, and we got the work from integrating the pressure, and so that was the isotherm. And so that should be it. So in my case, I would write this as NR, and I'll put TH. Oh, no, cold one, sorry. TC. This is the cold one I'm doing right here. And so my volume is from C to B. And let me put the bigger one in the numerator, which is C, because again I want this to come out to be a positive number, because that was kind of our discussion about absolute values there. And so I'll put C and then B. But there is the magnitude of the energy coming out from the cold part of the cycle. How about the hot part of the cycle? Now again, what kind of process is this? That's an isotherm. So wouldn't it still be this same equation? It would be nRT ln V2 over V1. It's just now when I write it, I'm probably going to write it at temperature hot and ln of, and then it'll be a ratio of the volumes. Again, making sure I put the largest volume on the numerator so that I have the absolute value, which would be C over D. Did I do this one wrong? Yeah. B is the big one, thank you. B over A, yeah. And then the other one would be C over D, there we go. And so that would be the heat coming out over there. Okay, now again, what am I after? Well, I'm after this 1 minus this ratio. Well, let's take a look at that ratio. The cold one is nRT cold ln of VB over VA. Okay? The denominator, as we are seeing, is nRTH ln of VC over VD. The N and the R are going to cancel off. What about these volumes, though? And they are going to be the same. Again, maybe it's not quite so obvious till we sit down and do this again. But there's two adiabatic processes here. And adiabatic processes are connected with temperature and volume, as I've written there. So let me connect these adiabatic, the A and the D. So this would be A, D, D. Let me also connect this adiabatic process, the B and the C. So B, C, C. This would be the temperature at B. This would be the volume at B, gamma minus 1. This would be the temperature at C. This would be the volume at C, gamma minus 1. Let me divide these two and look closely at the temperature at A and B. AB, what is I saying there? That's the same number, right? That's an isotherm. So A and B are the same number. They can cancel off. D and C, same thing. D and C are connected by an isotherm. D and C, they can cancel off. Everything, what's left, is raised to a gamma minus 1. So let's just raise everything to a power of 1 over gamma minus 1. And I end up with volume at A over volume at B being the same as volume of D and volume of C. Well, let's take a look. What's this saying? There's B over A, which would be the reciprocal of that one. This is C over D, which is the reciprocal of that one. Isn't this saying these are the same numbers? So ln of the same numbers cancel off. And I always find this quite surprising that it actually comes out to be quite simple equation. And it gives us something to strive for. What is the maximum efficiency you could get? If we were burning gasoline, we could sit down and say, okay, my automobile can never get better than this. We can find out what temperature does gasoline burn at, okay, and what temperature are we exhausting our gas. Usually comes out of the tailpipe warmer than the air around us, but in an ideal world, we would cool it all the way down to the world around us. And so maybe this would be 300, and I'm not sure what temperature gasoline burns at, say 700, but whatever this comes out to be, I bet it's got to be more than that. But whatever that comes out to be, that would be the maximum efficiency. Of course, I haven't proved to you, but I'm about to, that this is the maximum efficiency. But this is why we put a little sub C. This is the efficiency of the Carnot cycle. Keep it in mind that this then should come out to be more than, say, 60%. In fact, 60% is what I got with mine there. And so it depends on your temperature difference. Well, in the 5 minutes we have left, shall we do the entropy of this thing? Let's look at the engine first, then the environment. But like we did on the last one, let's look at the change of entropy in all 4 cases. What's the change in entropy of A to B? Well, that's the integral of Q over T. Here's the best part of this one. What kind of process is this? It's isotherm. What do you say about the temperature? Constant. I love doing integrals that have constants. So easy, right? Pull the constant out in front. Temperature doesn't change. And so this would be the Q of hot over the temperature of the hot. Right? That's the change of entropy. We could even continue this on. Didn't we actually calculate this number a moment ago? Right? It was, oh, I shouldn't have erased it. The N R T hot ln of the volumes, right? Work, and we did a P, yeah. And so what process is this? A to B, so this would be volume of B over volume at A. And of course, this would come out to be NR ln of volume at B, volume at A. So that would be the change in entropy from A to B. What would be the change of entropy from B to C? Right, that's another adiabatic process. We kind of discussed that one before. No change in internal energy here, or Q, heat energy. How about from C to D? Right, that would kind of be the same logic here. Maybe it's worth running through again. Then what's going to make this a little bit easier than the last calculation is it's an isotherm. Isotherm have constant temperature, so I can pull out the T. Then I would just have the integral of Q. So this just becomes a Q. Now this is the Q that comes out of the cold one. And then this would be temperature of the cold one. So again, not a surprise that those two look the same. And of course, then if we do this substitution, this would be NR, temperature of the cold one, times ln of final volume. And here we want to watch our signs. I know when I did efficiency, I was only working about absolute numbers. But here I want to watch my sign. And so as I go from C to D, I do want the volume at D over the volume at C, and then temperature over C. And so this is an NR, natural log of VD over VC. And then if I do my last couple of steps here, 1 minute, change of entropy from D to A, I should get 0. Looking at just the engine by itself, I would add these 4 together. Those 2 are 0, so that's easy. But as we pointed out, didn't this ratio and this ratio the same but flipped over? Isn't that what we just had on the board? So isn't this number the negative of that number? Here the energy is going in, so this is positive. Here the energy is going out, but that's positive, that's negative. The total of this engine is 0. Now that doesn't surprise you because it's an engine. It goes all the way back. Every engine as it gets back to where it started should have a change of entropy of 0, definitely. But that doesn't mean also the environment. And this is the last part I wanted to show you. This is where Carnot's logic comes into play. When he talks about the hot environment and then the energy going into the cool environment, since we've just done the engine, we should also ask ourselves about the other things. How much entropy came out of the environment when this went in? See, when this went in, this was a positive, so this should be a negative. What's the change in entropy of the environment here? Well, it would be QH going in, because isn't that what goes in? And doesn't the first law tell us they have to be the same energy going in? But the neat thing about it, it was at an isotherm. The environment probably didn't change. The environment is this big bath. It's this big hot water thing over here. And so what ended up happening is this is the calculation for how the change of entropy coming out of the environment. This is coming out. This is a negative number. But what did we say went in? Same thing, but a positive. And so because of the fact we were at the same temperature, we draw the conclusion that the loss of entropy from the environment is equal to what was gained by the engine during the hot part. Same thing here at the cold one. This would be QC over the temperature of the environment. And so that number is the same as that number. And so if you added up all the engine and the environment, guess what you get? 0. And that's why Carnot can say this is the most efficient engine. Nothing you could ever build would be more efficient than this. Otherwise it would violate the second law of thermodynamics. All right, well, good luck on this. Guess I'll see you Tuesday.